Basically, I'm going to tell you about entanglement and how it turns out to become important in condensed matter, and how this has finally led to all kinds of beautiful dreams about a new topologically protected quantum computing. Okay. So as we know, the laws of modern quantum mechanics really haven't changed since 1925 to 32 period. So, but what has changed is, once the laws are written down, it takes time to work out what exactly you can do with them. Same thing happened with Maxwell's equations. And all tests have shown quantum mechanics is correct, but what we now have learned is that it permits very cool things to happen that we wouldn't have initially guessed. So starting around 1980, there were new insights into quantum mechanics started to emerge, and new unexpected topological states of matter started to be discovered. And since no one had dreamt of such states before, they were quite a shock to us. But this has gone on and been combined with a lot of interesting ideas from quantum information theory that Feynman initiated about in 1959, I guess 60 years ago. And people now, as we heard on Saturday, on Sunday, I guess, Saturday we're talking about a second quantum revolution, a whole new set of ideas for looking at and interpreting quantum mechanics and coming up with things that you can do with it. So classical information is stored in a simple bit, a switch, which is either on or off. But quantum information can be stored in this new idea of the qubit, which is a generalization of the idea of a single two-state system or an electron spin. And while a spin can point in two directions relative to some axis, that axis can be allowed to move around and point in any direction. So there's a lot more subtle ways to incorporate information into the Bloch sphere by an arrow that points on the Bloch sphere. So the central theme in these new approaches to quantum mechanics is really the property of entanglement. And when I started off, we really didn't think much about entanglement. Entanglement was a problem for philosophers of science, and discussing whether quantum mechanics was compatible with free will and things like that. But now we really recognize it as perhaps one of the central properties of quantum mechanics. And of course, it was initially pointed out as important by Einstein, but now we're thinking of it as the fuel which will drive future quantum information processes. So of course, Einstein got his Nobel Prize not for relativity, but for the photoelectric effect, for his early contributions to quantum mechanics, but by 1935 he was really rejecting the quantum theory by thinking it couldn't possibly be a true fundamental theory. And he identified the key property of entanglement, which he thought was so strange that it couldn't possibly be right. So he was hoping to consign quantum mechanics to the dustbin of history by pointing out the crazy things it predicted. And he called it, of course, spukhafte Fernwirkung, spooky action at a distance, but Schrödinger came up with a much more neutral term that we use, which translates into entanglement. So, of course, one of the fundamental properties of quantum mechanics is the Pauli exclusion principle, that says that two electrons, which are fermions, can't be in the same state. But in addition to position and momentum, the state of electron also depends on this internal degree of freedom, its spin, which is analogous to the spin of a top. And of course, the chemical bond, which holds us all together, is the way that the Pauli principle is overcome, because the two electrons can fit in the space between two atoms to form a chemical bond to hold us all together, because it has these two different states of the spin. So the poster child of entanglement is the chemical bond, which is the maximally entangled state of two electrons, where we have up and down. One electron is up and the spin, and the other electron is down, but the quantum mechanical state is a superposition of the two possibilities, up, down, and down, up. And this is the maximally entangled state. But of course, what Einstein was worried about was if the chemical bond was stretched to large distances, maintaining this curious correlation between the electrons, that it was a superposition of up, down, and down, up. He felt, if you do a measurement over here on this electron, how could it possibly be compatible with relativity that immediately implied that a change in the other electron? So he felt this quantum state of entanglement at large distances couldn't possibly be a true state. And it superficially looks like it might violate the principle of relativity, that information can't travel faster than the speed of light. But when you analyze this more closely, you cannot send information between the two experimentalists instantaneously by doing a measurement. So it's not really a violation of relativity. So this puzzle that Einstein, Podolsky, and Rosen produced got analyzed in great detail by people like David Bohm and then finally John Bell. But finally, when the experiments were done, quantum mechanics passes with flying colors. In fact, the only let-out clause are still discussions about the free will of experimentalists in choosing which axis to measure. But so anyway, the problem is entanglement over large distances is very fragile compared to the chemical bonds. And so electrons also interact strongly with the environment. So these experiments to prove the Einstein-Podolsky-Rosen effect or entanglement could exist at large separations have been done with light. But it's totally convincing now, and indeed we just heard on Saturday from Jianwei Pan about the work in China where we've created entanglement between the ground and orbits and satellites in orbit. Okay. So around about 1980, the condensed matter physicists were kind of arrogant enough to think they had a basic understanding of electronic and magnetic materials. But around that time, there were kind of two examples which initially had no obvious connection whatsoever to each other, although it turns out they both involve the Berry phase, came up, and they were both very unexpected. So the first of these things was, of course, the discovery of the quantum Hall effect by Klaus von Klitzing, a completely unexpected effect, which shocked people at the time. And the other thing was some work I did on low-dimensional magnetic systems. So these can be viewed as the tip of the iceberg in this iceberg metaphor. But in the succeeding decades, many, many more new kinds of topological materials have been found, and a unity which relates these two effects has been found. And of course, the most exciting aspect of all this has been probably that the ideas about topological quantum matter have led to a proposed platform for topologically protected quantum computing, which at least theoretically provides a nice way to have scalability with and avoiding decoherence, which other non-protected versions of attempts to do quantum computing don't have. So what's topological matter? Topological matter differs from ordinary matter because it has properties which really are probably entanglement properties that can be described by whole numbers, like integers, like -1 or 2, etc. So the basic issue is that states of matter which are characterized by an integer can't smoothly change from one to another. Something always has to happen at the boundary, and it's usually something pretty interesting that happens on the boundary between different types of matter. So here in the picture we have boring matter, which I've assigned the index 0 to, and some non-trivial matter. Now, of course, 0 is not exactly a boring number. It took a long time to be discovered, but it's what we might call topologically trivial. So the boundary has to be there. And basically, that's because its topological properties cannot change continuously. And a key aspect of that is it makes the properties robust to small amounts of disorder or dirt in the material, which is a contrast to the usual material properties of which our current silicon technologies for information processing are based on, which require ultra-clean preparation. A single speck of dust or a hair or something on the silicon chip will ruin it, which is why people have to be dressed up in these spacesuits, not to protect them from the nasty chemicals in the foundry, but to protect the valuable silicon wafers from the people. So the classic example in mathematics is the classification of closed surfaces by what's called the genus, or the number of holes in them. And this was a metaphor that was being used by the Nobel Committee to try to explain to the public what topological matter was, probably with great confusion arising. But a shape like a sphere with 0 holes, you can distort a sphere, you can distort a football into a rugby ball with small forces, but if you want to change it into a donut, an object with a hole, you have to do a significant amount of violence to it. And so holes come in whole numbers. You don't have to say there's such a thing as 0.36 of a hole. So they're easy to, you either have it or you don't, basically. At least, of course, when you get down to the atomic scale, the things are not smooth anymore, so there's actually usually a length scale involved where things become topological on a sufficiently large length scale, which turns out to be a crucial point. So topology comes from the great discovery by Gauss, who discovered basically that 4 pi r squared, the area of a sphere, times 1 over r squared, its Gaussian curvature, was 4 pi. This is a kind of high school formula, but what Gauss discovered was if I changed my sphere to the rugby ball or even to a banana, that number stayed the same. And in fact, you could do a very complicated integral of the curvature, which on a non-uniform surface can be positive in some places and negative in others, and get this simple number. So a sadistic high school mathematics teacher could give very complicated problems to the students, but he would know if they got the right answer or not quite quickly by just checking what multiple of 4 pi they managed to get if they managed to do it. So in this picture, we have this famous picture which usually shows the bagel turning into the coffee cup, which every experimentalist working on topological matter cannot prevent themselves from showing at the beginning of their talk. This simple idea has been so exciting to people working in the field, they just love the coffee cup metaphor. Well, of course, in Sweden, they were trying to talk about something which wasn't really a pretzel. It was actually a Santa Lucia bun with 2 holes in it, which would be topologically equivalent to what's called a loving cup. But actually, when you bake the Santa Lucia bun, the holes actually fill in, so it's really a fake pretzel. And the real pretzel, of course, is the German pretzel with 3 holes, and which is equivalent to this interesting cup here. I'm not sure what it's called, but I did hear it suggested to me this was a California loving cup. Anyway, the mathematicians, of course, love to take a simple formula and make it much more general and much more abstract. And indeed, the Gauss-Bonnet formula was generalized mathematically from a physical curvature on a real surface, embedded surface like the bagel, into a much more abstract mathematical curvature on much more abstract surfaces which could occur in any even number of dimensions. And so this actually gave rise to the Gauss-Bonnet-Chern formula. Now, the mathematicians don't have a Nobel Prize. The nearest thing they have to it is the Fields Medal. And maybe there's some Fields medalists here, I don't recall. But the Fields medal is a very kind of ageist thing. It's discriminatory because you can't get it. However good your math was, you can't get it if you're over 40. So they invented a couple of new medals, one the Abel medal and the other the Chern medal for kind of old-timers. And back on the Chern medal, of course, is the Gauss-Bonnet-Chern formula inscribed. Okay, so what is the entanglement in a quantum mechanical context? Basically, if you take normal matter, trivial matter, you can do a measurement on one side of it without really affecting things that happen on the other side, and so you can kind of pull it in half quantum mechanically and get a product state. But because the topological matter always has these edge states, it resists chopping in half, and eventually, when you do manage to split it, the edge state has spread over the new surfaces. So you can't avoid having these edges. And so basically, topologically trivial states of matter can, in principle, be assembled just by bringing the atoms together and stacking them next to each other. While if something non-trivial happens, the electrons kind of get unbound from the atoms and rearrange themselves somewhere along this path of constructing the matter. And in fact, once this principle is seen, you can see it in old work. In fact, this is an example going back to 1939, where people shockingly managed to do a calculation of toy model of a one-dimensional chain of atoms. And what you see as you bring these things together, the energy bands which were initially the atomic levels kind of broaden, but they come together and they split up again, and you get these new topological edge states at the system. You have one at each side of the sample, and they have very interesting effects, such that if you try to fill this with electrons, you're more likely to have the chemical potential below or above these two states. So you either have one electron too few or one electron too many compared to the original atomic system, and that extra electron is split in half. One half of it goes at one side and one half goes at the other side. And that's a very typical thing associated with the topological edge state. So this would actually be what we now call a symmetry-protected topological insulator. So in heavier atoms, electrons in a group of atomical orbitals can be locked together, so they're always parallel, and that gives rise to magnetism. The elementary spin has got angular momentum, a half h-bar, and so the total spin will be a whole number which is either even or odd times a half to make an integer. And conventional magnetism, you just stack these magnetically ordered systems together, but there's no real entanglement in them. But what I discovered by basically looking at this problem from a different viewpoint, usually one has some history where one's coming to a problem. I was working on some other issues in one-dimensional organic conductors and applied some results from that to the magnetic problem. So I was shocked to find that the conventional wisdom about what these magnetic systems should do was like 100% wrong. It was actually wrong because people had been confirmed in their incorrect ideas by apparent evidence from an exactly solvable mathematical problem, but the problem was they'd completely misinterpreted what that exact mathematics was telling them, and it confirmed them in their prejudices. So I'm sure there's plenty of other things that we believe in which are wrong, and we think there's pretty good arguments for them, and you may be the one who one of you may be the one who finds out that everyone else was wrong and changes our way of thinking. Okay, so this was a very controversial thing, and it shocked loads of people, and again, there was a lot of resistance to it. But finally, physics is not a question of opinions, and experimentalists, especially material scientists who managed to motivated to actually make the systems to fit the theorists' ideas rather than the other way around, they came up with ways to actually make these magnetic systems, and finally the experiment showed that the new kind of states were correct. And it led to, the actual controversy led to people coming up with lots of new ideas and new methods for studying problems, which have turned out to be very important. So the metaphor here, which you'll see, is that we have a line of if we have a line of people who become entangled by holding hands, you apparently get left over with a spare pair of independent hands at either end of the system, where if a person hadn't had a bad accident, you'd come up with the idea that hands always come in close pairs. Okay. And of course, this led to this prize business. So soon after this discovery, the underlying mathematical principles came out, this fundamental idea of the Berry phase in quantum mechanics, which is really at the heart of all the kind of modern physics that we've been talking about. And initially that came up in quantum spins. But then at the same time we had Klaus von Klitzing had discovered the quantum Hall effect, which, as we've heard, has now become the system at the base of the new system of units for replacing the kilogram. And this is electrons in a high magnetic field moving around in little circles. And it wasn't initially clear where topology came into this, but as was pointed out by Bert Halperin, you have things going around in little circles in the interior, but if you hit the boundary, the circular trajectory, which leads to quantization, is broken, and in fact you get these edge states that move around. And now we understand that edge states are very typical of topology. David Thouless was working on this problem with collaborators, and they did the important step, which I kind of do too, which is to replace difficult problems with toy models that you can actually do a calculation on. So they replaced the more complicated problem of disorder in a real system with a simple periodic potential, which is the kind of thing we can solve. And they came up with a beautiful formula, which basically showed that the whole conductivity was still given by an integer times e squared over h. And the mathematical physicist Barry Simon heard on the one hand about Berry's calculation, Berry's phase. On the other hand, he heard about this numbers that Thouless has formula, and he put two and two together and realized it was all the Gauss-Bonnet-Chern thing. And that was that. So it used to be thought that initially that you needed high magnetic fields to get this quantum Hall effect. Maybe it should have been realized from Thouless's result that that wasn't necessarily true, but somehow as an accidental discovery, almost like the accidental discovery of the spin chain business, realized that you could actually get rid of the magnetic field completely and just keep Berry curvature in the problem and get, with standard crystalline materials, and get interesting topology, including edge states that go around one way on the boundary. And so this is actually, again, not obvious. Most interesting things are not obvious even to the people who discover them, right? But that's the nature of things. So, yeah, when one looks at the details, you see lots of interesting things going on that I'll have to skip. But this actually shows how long it takes to find something out. It was actually predicted in 1988, and it was a theorist's toy model for a long time, but finally it led to other things, and finally those led to the experiments which were done only in 2013 to show these effects can happen. So again, without huge magnetic fields, this so-called quantum anomalous Hall effect gives rise to these edge states which move in one direction, and actually that seems to have a lot of very interesting technological possibilities. In fact, one can actually, from this edge state aspect of things, you can put aside the quantum mechanics, because while some aspects of the quantum system of course require Planck's constant, the integers don't, and the existence of edge states turns out to be there in photonics too. So the simple toy model I showed you has led to lots of new things, both in photonics and also mechanical systems. So there's actually surprising amount of new work going on. You know, once you realize the principle is there and is quite general, it's very beautiful. It was, of course, generalized to spin systems without magnetism by Kane and Mealy, which initially provoked this large revolution because that led to lots of materials actually being initially discovered. They were sitting on people's shelves, but no one had looked at the edges clearly enough to see there was something different about them. Okay, and this led to all kinds of new things, which I can't go into. So where does the quantum computing come from? The integer Hall effect was now followed by a much bigger puzzle, the fractional Hall effect. And here you see the sample in which the fractional Hall effect was discovered, which kind of, by looking at it, you can see how the robustness of topological physics against disorder, right? I guess this wouldn't have got Art Gossard. Well, whoever did this probably wouldn't have got a job in the clean room making chips with their soldering skills. But anyway, so lots of really interesting things happen in the fractional quantum Hall effect, non-abelian statistics, fractional charges. But the most remarkable aspect is actually what we now call non-abelian quantum statistics, which is what this gives us actually the ability to hide information in the entanglement structure of systems. And that's really what was made people so excited about the possibility of a protected form of quantum computing. So the proposal for that goes back to Alexei Kitaev, who looked at work of Moore and Reed, who came up with the first of these non-abelian states. And basically, you do something called braiding, where you move vortices or little defects in this system around. The quantum Hall system is like a quantum fluid with little vortices, which are little whirlpools in it. And the information I'll show you is actually stored in the history of how you prepared the vortices. So basically, these little objects can only be created in pairs. So you have to create two of them at one place and then pull them apart. So here I've got a system which apparently has the same configuration in real space of the four vortices, but hidden in it is the history of how these configurations were produced. And these are the entanglement patterns, and this would represent one state of the qubit, the other one would be another state rotated by 90 degrees on this Poincare sphere. And in fact, when you look very closely at a calculation of these systems, so this is, again, a calculated toy model system with four of these vortices arranged on a sphere, in fact. But you can see one state might be the up state of the qubit, and the other might be the down state of the qubit, or a linear combination of them would be the sideways state. And you can see, because they're not infinitely far apart from each other, there are little interference patterns that distinguish the states. So the information is actually in the interference pattern, and in principle, it's not completely hidden, but the wiggles you see become exponentially weaker and weaker as I move these things apart. There's always a length scale involved. Topology happens when things are infinitely separated on a microscopic length scale. And here you can see the information becomes more and more delocalized and more hidden as you move things apart. So it's the magic of how it is really encoding in interference patterns. So the quantum physicist's beautiful dream of topologically protected thing is qubits is just one way to maybe overcome this problem of decoherence. Of course, there's lots of other attempts to do quantum computing, and everyone is competing. So I personally believe that topological quantum computing is a realistic dream, but we'll find out. The current scheme for topological computing is actually based on superconductivity and so-called nanowires. Again, it's very similar to what I showed before with the spin chain. Again, if I put electrons in contact with a superconductor, it somehow allows the electron loses its charge into the superconductor and then can actually split up into two kind of half electrons called Majorana modes. And by joining these things up together in one way, you actually can end up with what you think ought to be indivisible, an electron state, which should be able to contain one electron, actually split up into two pieces on either end of the sample. And that leaves a string of entanglement between the things. So the metaphor of the chain of people is quite similar. So again, there's lots of other attempts to do things in quantum computing. Lots of people are competing, so I don't know what will happen. But finally, I just come to the motivational message. Again, like Mike Kostelitz's, you don't actually have to be a great genius like Einstein to get a Nobel Prize. I mean, of course, the really satisfying thing is to find the result rather than get these kind of prizes. But basically, anyone doing research can potentially end up with a Nobel Prize to be on this stage. because you do need luck. On all these discoveries that I've had the fortune to be involved in, at least the two of them I showed, they were looking at some problem from a different viewpoint, and allows you to gain some aspect of it that wasn't the usual people working on it hadn't noticed. So, but you do need luck to stumble across something. Often you'll find something which is interesting, and you need to take the time to look at something unexpected and interesting. Most of the time it'll just turn out to be an amusing curiosity, but very occasionally it'll turn out to be something that no one had thought about before and no one was looking for, so it was out there. There was no competition to find it because no one was looking for it. Of course, you do need the preparation to recognize what you've seen and some kind of... so the preparation is important, and you actually do need commitment, because typically if anything is sufficiently interesting and new, it gets a lot of resistance initially, as we heard from Mike. And these are probably the same things you hear about in any businessman giving an inspirational talk about how to succeed in business. You need luck, commitment, and preparation. But anyway, I think you all have the chance to discover something interesting, and sometimes something incredibly amazing. Obviously, it's a very small chance of finding it, but you've all got it. Thank you.